Hey physics students, in this lecture we're going to talk about projectile motion. So, to start out we got to talk about what a projectile is. And in physics when we talk about a projectile we're talking about an object that the only force acting on it is gravity, which means that projectile will always have an unbalanced force on it, and it means that it will always accelerate in the direction of gravity. Now in most real world situations there's always going to be other factors such as air resistance. But there are a lot of situations that are closely estimated if you assume that gravity is the only important force acting on them. So whether it's the skier or the bouncy ball you see in these pictures or the water in the fountains on the slide previously, those could all be closely approximated using projectile motion calculations. So what are some tricks for solving projectile motion problems? The first and most important one is that horizontal motion and velocity is completely separate from vertical motion and velocity. They don't affect each other. So if we look at the balls in these two videos, one is dropped straight down, the other is, say, rolled off the edge of this table at an angle. And even though one is traveling horizontally and the other isn't, you'll see that they're always at the same height. They are always following the same distance, and you can see that the distance in between these balls keeps increasing, meaning that it's speeding up as it falls. So if something is at terminal velocity and is no longer accelerating, that is no longer considered a projectile because there is a significant air resistance force affecting it. We'll talk about a few more tricks for solving these problems as we look at individual problems, but first let's take a look at what equations we have to use to solve these and when we can use them. So there's velocity final squared equals velocity initial squared plus 2 times the acceleration times the distance. We have velocity final equals velocity initial plus acceleration times time. Change in distance equals velocity initial times time plus 1/2 acceleration times time squared. And we have change in distance equals velocity times change in time. And any of the other kinematic equations can be used to solve these problems too. So when do we use these? If you look at these two equations, they're very similar. Both involve velocity final and velocity initial. The difference is we use this equation when you want to know the final velocity but you don't know the time. However, you do know what the distance it accelerated was. You would use this equation if you want to know the velocity final and you know what the time was. So one involves using distance to calculate final velocity, the other uses time. This equation is for finding the distance it traveled when we know both the velocity initial, the time it accelerated for, and the acceleration. And this is how we calculate the change in distance when there is a constant velocity. So if there is no acceleration, we use this equation. And by the way, in this one there has to be a constant acceleration. It doesn't work if the acceleration is changing. Okay, so let's practice a few problems. As we step through this, they're going to get basically 3 types of problems, and they're going to get harder and harder and harder. We're going to start with the simplest one, which is just one that has no initial vertical velocity. It's a horizontally launched projectile. So something, let's say, that's kicked off a cliff horizontally, or rolls off a table, or slides off a road, something that is not moving upwards initially, and just has an initial horizontal motion, but then gravity is the only force affecting it. Then we're going to move on to one that's vertically launched but that lands at the same height, and then we're going to move on to one that's vertically launched and then lands at a different height than its launch. So, a horizontally launched projectile. The bad guys in car A are chasing the good guys in car B as they come around the turn and approach a cliff. Car B is moving at 31.7 meters per second, and car A is moving at 35.2 meters per second. They both go horizontally off the 17-meter high cliff. Which car lands first and how far apart do they land? So first of all, we can answer the first part of this question, which car lands first, without doing any calculations whatsoever, because we know that they leave the cliff at the same time, and we know that horizontal motion does not affect vertical motion. So if these both have zero initial velocity in the y direction, they're going to hit the water at the same time, just at different distances. So neither car lands first. The second question, how far apart do they land? Okay, so we know that we can separate, the first trick is always to separate the vertical components and the horizontal components. So as I'm thinking about solving this problem, I know that because horizontal motion doesn't affect vertical motion, I can use the acceleration due to gravity to find how long it takes to hit the water. And once I know how long it takes to hit the water, I know how long it will travel sideways at a constant velocity, for example 31.7 meters per second. So let's do car A first. Oh, hold on, my pen's messed up here. Okay, so the first step in solving this problem is to find out how long it takes to hit the water. So we start with our initial vertical velocity, so Vy initial is going to equal 0 because this thing takes off in a horizontal direction. And we know the acceleration is going to equal 9.8 meters per second squared, the acceleration due to gravity. And we also know the change in distance. They are falling off of a 17-meter cliff, so that's going to be the change in distance. What we need to know is how long does it take to hit then. So we know that change in distance is equal to velocity initial times time plus 1/2 acceleration times time squared. And we also know that my velocity initial is 0, so this falls out. And now change in distance just equals 1/2 acceleration times time squared. So I plug in my numbers. 17 equals 1/2 times 9.8 times t squared, and solve that for t. And we get that t equals 1.86 seconds. So now that we know how long it's in the air, we can figure out how far it goes horizontally. We know that for car A it's moving 35.2 meters per second. So change in distance when you have a constant horizontal velocity, because it's not, remember, it's only accelerating in the vertical direction, not in the horizontal direction. So change in distance equals velocity, if it's constant, times change in time. So it's going to equal 35.2 times 1.86 seconds. So it equals 35.2 times 1.86, 65.5 meters. Now let's look at car B. It's going to be in the air for the same amount of time, again because horizontal motion does not affect vertical motion. So we just have to use change in distance equals its velocity, 31.7, times change in time, which is 1.86 still, and 31.7 times 1.86 equals 58.96. So we're not quite done. They said how far apart do they land. We take the two distances and take 65.5 minus 58.96, and we get 6.5 meters is how far they'll land apart. Okay, so for almost every horizontal motion problem, you're going to start by finding the change in time, and then you'll use that to find the horizontal distance that it falls.